Our next set of speakers are coming from NYU, Damian Ekiert and Gira Bhabha. And I think the main thing to think about is that what are we going to do with maps now that we're in structural biology, where we were sort of technologists and sort of biologists coming at the issue. It's not that we skipped model building, it's just that until recently, we didn't have the Coulomb potential maps that we would want to make those testable models. I would say we have plenty of time for additional Q&A after the talk, and Ollie will join. And something that I would ask would be, you can talk to Gira about her favorite ice cream restaurant in San Francisco, or you can talk to about Damian about what he adds to his vanilla ice cream. The floor is yours.
Okay. All right. I think I got the mic on screen. So, okay. So really, like going hand in hand with what Ollie's been talking about, the actual building of your model. Also, there's these two other really important parts of the process, right? Which is the refinement of your model and validation of your model. And really, I think you should not be thinking of these three things as like three separate processes, but three things that are all kind of intermingled together and like something you cycle through over and over again. And so validation in particular, some people think it's like something you do at the end, but it's really something that's sort of after each round of model building and refinement by running your model through some validation programs and identifying the problematic areas. It will help your next round of rebuilding and help you to kind of correct errors early on. So I think Ollie mentioned something kind of similar to this already, but in terms of model building, but also in terms of refinement, the ultimate goal is we're trying to make a model that best explains all of the data we have, but at the same time also looks like what we know proteins should look like, right? And so that applies to model building as well as the refinement process. And so I'm going to use this analogy kind of through the lecture today. There's a lot of kind of parallels between refining your structure and kind of protein folding funnels that you might have heard about in kind of biochemistry class. And so in protein folding, we think about a protein that starts in an unfolded state that's kind of high in energy, and then it slowly folds up and adopts its kind of lowest energy conformation down here at the bottom of this well. And so we see these funnels that show the kind of energy landscape of a protein and all these different potential states that the protein can occupy. And so we have kind of this energy function on the y-axis and all the different conformations along this surface. So you can think of refinement and building of your structure in a sort of similar way, where you start off with a model that has some sort of problems. It's not in its lowest energy state, and you can, through rounds of rebuilding your model and refinement, you can slowly improve that model to get it to the final kind of best model you can possibly create that hopefully best reflects the original protein in the cell. And so instead of kind of a pure energy function on the y-axis here, we have some kind of target function that kind of tries to describe what a protein should look like and how well this protein matches what we know protein should look like geometrically, and also how well the protein matches your experimental data, so your density map. Okay, and so what this refinement target is, we won't talk about in a whole lot of detail, but it includes a whole lot of parameters that we'll kind of touch on. Okay, and so just boiling it down to kind of the most basic level, so this refinement target could essentially be just looking at how well the model you've built agrees with your experimental density map, right? And so you could imagine you could take your model, calculate what the Coulombic potential would be from your model, and compare that to your experimental map, and just say how similar or different are these, right? And quantify the difference. But we can add on a few additional things to that, and we'll talk about that a little more. So the problem is that, and Ollie also showed you a really high resolution structure like this. So when you're at extremely high resolution, you can really just rely entirely on your map, right? Because there will be information that specifies the position of every atom with really high precision. And you can basically just ignore what all prior knowledge and say, we're just gonna let the map tell us where the atom should be. But it's exceptionally rare, both by X-ray crystallography and EM, that you ever get to a map like this. And so in practice, this is probably the kind of typical map that you'll be looking at as you're working on an EM structure. It's a pretty nice map. You have density for a lot of side chains, but things aren't always perfectly clear. But you can kind of generally get a sense of where things probably should go. So if you were to try to refine your model in a map like this with no prior knowledge, only using the map, you'll probably see something like this. So here in COOT, I just turned off all the geometry restraints I could and tried to refine this one residue. And you can see it basically just collapses into a spider web of mess, right? So we obviously need to put in some kind of other prior knowledge for these refinement processes to work. So that function we're going to try to optimize can't just be model versus data, right? We're going to have some other terms in there. And I think this is a just similar sort of movie, like doing this with kind of like a whole alpha helix. So if we kind of turn off the restraints and try to kind of just real space refine this region in COOT, you can probably kind of guess what happens, right? So we get something that still kind of follows the density. So it's kind of consistent with the data, but definitely is not what a protein should look like. Okay. So we have this sort of continuum where at really high resolution, I'm going to try to point here rather than walking to the screen. Okay, so when you're at really high resolution, we can trust our data almost entirely and pay very little attention to prior knowledge. But we're very rarely in this regime. At the other extreme, this is sort of like AlphaFold, right? So this is like we have no data or exceptionally low resolution data, and we have to rely extremely heavily on prior knowledge, right? So if you're at 20 angstroms, you can't even tell where secondary structure is, so you need to be able to predict domain folds, right? And be able to place them in a low resolution map. And then somewhere in between, we have to kind of figure out what the right balance is between these two sets of information. And so most often, this is where we're working, where we're using some balance of our experimental data and all of this prior knowledge to try to get the best possible structure we can. And so that refinement target then becomes, some parameter that includes comparing your model to your data, but some parameters that are also comparing your model to that prior information. So known folds, known secondary structure, known stereochemistry. And this can be a whole list, so comparing to, stereochemistry can be a term, secondary structure can be a term. So you can have a series of terms and each of those can have a weight, right? So then we can decide how much are we going to trust the data, how much are we going to trust prior knowledge for each of those terms. Okay. In practice, you don't really have to, set those weights yourself for the most part. They tend to be kind of handled automatically in the refinement packages, but there are some times that you can potentially try to intervene if you're having problems. Okay, so what is all that prior knowledge? Just really quickly, I want to run through. Okay, so of course there's all sorts of stereochemical knowledge about proteins, so we know what they should look like. We know how long a CN bond should be, what the angles between different atoms and bonds should be. We know peptide bonds should be planar, right? So these should be either 180 degrees or 0 degrees rotation about this bond. And proteins are chiral, right? So it's we're almost always dealing with L amino acids in our proteins, right? We don't have D amino acids. So all of these things kind of guide our building process. And then of course, rotatable bonds have, they can't freely rotate and be at any position, 1 degree, 2 degree, 3 degree. There's kind of preferred rotameric states. And so we can restrict the protein to adopt only these preferred rotameric states. Secondary structure, of course, there's lots of secondary structure in proteins, so we can restrain our model in areas that we think should be alpha helical. We can restrain them to be helical, and we can do this either by restricting those rotatable bonds, the torsion angles, such that the peptide backbone only adopts helical geometry, or we could also potentially restrain based upon hydrogen bonding patterns, so we could say that, the hydrogen bond donor has to remain within some distance of the acceptor. And you can imagine that could work well for beta sheets as well. So either enforcing the hydrogen bonds between adjacent strands or by enforcing the geometry within each strand in torsion angle space. Okay. Another kind of prior information we can bring in here is something that, going back to crystallography is referred to as non-crystallographic symmetry. And so we can take advantage of this in the case where the structure you're working on has multiple copies of the same protein, right? And so sometimes if you have something that's truly symmetric, right, you might have already taken this into account in your map calculations, right? So you may actually have already applied symmetry in your reconstruction if you're working on the proteasome, right? So you have this D7 symmetry. So you might already have an asymmetric unit. Your map might only cover like 1/14 of that structure. But it's not always the case. So sometimes it might be that your particle is asymmetric. So even though you have 6 copies of one subunit, it might be bound to another protein asymmetrically. And so non-crystallographic symmetry allows you to restrain those multiple copies of that same polypeptide to be very similar to each other in structure, or in some cases identical. And so in Phoenix, real space refine, which is mostly what I'll focus on today because that's what I have the most experience with, you actually don't have the option currently to restrain 2 chains to be similar to each other. That you actually can only force them to be identical to each other. So that can sometimes affect your decision making about whether you want to use this approach. Because if you have 2 chains that are structurally very similar to each other but not quite identical, you might actually be forcing them to be identical when they're not. More historically, in X-ray refinement packages, you often had a choice between restraints, which have some flexibility and can allow you to keep the chains to be very similar to each other, but not absolutely identical. So that might be something to kind of watch out for in the future. But this is another kind of prior knowledge you can bring into the refinement process. Another restraint we often apply is at the level of B factors or ADPs. So that stands for atomic displacement parameters. And the idea here is that if we look at a protein structure, it turns out that the B factor of one atom is not completely independent of the B factor that it's covalently bonded to, right? And one residue in an alpha helix, its B factor tends to be very similar to the neighboring residue, right? So we can sort of say that, okay, well, we're not going to let the B factors of each atom to vary completely independently of each other. We're going to say if you're bonded to another atom, we're going to restrict your B factor to be similar to your neighbors, right? And so this can help a lot in keeping your B factors from just exploding and making sure that they're sensible at the end of the day. Okay, steric repulsion, of course, so we know that atoms shouldn't overlap. So in refinement, we're going to try to keep non-covalently bonded atoms from actually physically overlapping. So if we were to sum up those 2 van der Waals radii for these atoms, they should kind of just touch under optimal circumstances, not really overlap. Okay, and so we have all these different bits of information, right, that we can try to combine during the refinement process to make the best possible model we can. And so data is obviously a major part of that, your EM density map, but all of these other sort of factors can come into play in different refinement protocols. And so that refinement target function, like I said, can become this long list of terms that sum up the contributions of all of this prior knowledge in addition to your data. Okay, and so in refinement, right, so we're starting from that initial model that we can think of almost as like a high energy state or an unfolded protein. And in the refinement process, we're trying to move it down to the best possible model we can generate that we can think of as sort of the lowest energy state. And effectively, that is the model that best agrees with this refinement target function that we're monitoring. Okay, so we're going to talk a bit about Phoenix Refine. So this is kind of, I think, still the most widely used refinement package for X-ray crystallography as well as cryo-EM data. There are other software packages out there. So RefMac is probably the next most commonly used one. So I definitely encourage you as you're continuing through your careers, always have your eye out for the newest, latest, greatest thing that comes out, because there's still, I think, a lot of innovation going on, especially for EM structure refinement. And actually, Ali mentioned iSoldy, which I think there's starting to be a little bit of blurring between it used to be you would build your model and then you would refine it, and things like iSoldy. Actually, I've never really known how to say.
I'm assuming it's from Tristan and it's all like not 100%.
Okay. Isolate, yeah. So COOT, you basically adjust your model and you can put it into Phoenix Real Space Refine and refine it. Whereas Isolde is a bit more in real time. You can adjust your model and there's kind of molecular dynamics going on, and it can relax, right? So it kind of starts to combine the two. So anyway, so always try different things. And I think with all stages of the cryo-EM structure determination process, I mean, there's like multiple software packages, and sometimes one will work better than others, right? And the same can be true for refinement. So definitely explore other options. Okay. So here's a screenshot of kind of the main page of the GUI from Phoenix Real Space Refine. How many of you have already refined a structure? So about half or a third of you have refined a structure so far. Yeah, so there's a decent number of parameters here on the main page. There's actually a huge additional amount of parameters that are kind of hidden from view, and we'll talk a little bit about some of those later on. But really the key parameters and the things you should start playing with are here kind of on the first tab. And so we're kind of going to work through some of these just so you have a better sense of what these various things mean, and maybe some strategies for how to approach model refinement. And so up here at the top really sets up the kind of like overall kind of approaches that are going to be taken to refining your input coordinates. And so we're going to talk a little bit about what each of these things mean. Okay, so minimization, global, rigid body refinement, local grid search, morphing, simulated annealing, and ADP refinement. Okay, so you've got your map, you've got some kind of starting model, right? And so one of the first things anyone is going to do is just rigid body fit this into the map, like Ali was talking about, right? And so often we'll do this in Chimera. But once you've got kind of most of your map filled up with these rigid body chunks, usually I'll take these into Phoenix Real Space Refine and do rigid body refinement there as well. And so you have a few different options with rigid body refinement. So, cryo-EM, right? We're typically dealing with these large complexes, multiple chains, or maybe each chain has multiple independently folding domains, right? So you can rigid body refine your entire complex at once, right? But in reality, quite often, individual domains will have moved relative to each other, between your starting model and your actual target structure here. So usually I will divide my model up into kind of all the individual domains that I think potentially could move independently. Sometimes you may know that these 5 domains always move as a chunk and they don't really move relative to each other. So you could define that module as a rigid body. So you can divide up your model in the way that you think makes the most sense, rigid body fit all of those domains into your map. Okay, so there were several other options there, so that's kind of the most basic. So the kind of next most basic refinement protocol is gradient-driven minimization, okay? And so going back to that sort of energy landscape analogy, you can imagine that, there are going to be these kind of valleys and peaks in the energy function you're trying to minimize. And so if you just allow the model to relax into the closest local minimum, so here's your starting model. So we can allow it to basically just slide down this slope into the nearest local minimum, right? And so the model's getting better during that process, so it's good. But if this ultimately over here is the global minimum, that's the best structure we can possibly build and refine, right? Somehow we need to get over to there. And so we need other kinds of refinement protocols to get there. So while gradient-driven minimization is something you will probably have checked almost every refinement job you do, sometimes you're going to want to use some of these other options. Okay, and so what are those? And so really the challenge and the reason you want to use those others is a problem called the radius of convergence. All right, and the idea is that depending upon the refinement protocol you use and how much you are kind of like, you could think of it almost like how much energy you put into the system to perturb things, refinement will be able to jump more and more of these peaks to ultimately get over into the global minimum of the energy function, right? And so whereas simple kind of gradient descent will get you into the nearest local minimum, we need to be able to somehow, like, that alone won't be able to hop over this barrier into the next one, right? So we need these other approaches. And so one of the oldest approaches that's been used for a long time is simulated annealing. And the idea here, this is kind of the best movie I could find. I know it's a little blurry. But the idea here, right, is essentially you take your protein and you heat it up, you put in a bunch of energy, so now it can move around a lot more and sample a lot of conformational space. And then we slowly let it cool down, right? And so as it cools down, it has the potential to, well, so when you heat it up, it has the potential to jump over one of those high energy states and cross into one of these adjacent lower energy local minima, right? And so by doing this multiple times, heating your protein up, letting it jiggle around kind of wildly, and cooling it back down, you can potentially jump over a series of these local minima and get closer to the global minimum. Okay. So that's one approach. There's a couple other approaches that also kind of try to solve this problem. So one is kind of a grid search in torsion-angle space. And so by grid search, this really means, so if you're searching for a lost puppy, right, it's like, you'll have people kind of checking like each of these big tiles in the room, right, saying, is the puppy there or not? So we can do kind of the same thing in terms of conformational space of a protein, right? So with the simple, one of the simplest side chains, serine, it has 3 different rotameric states for the side chain. So we can just test all 3 of those rotameric states and say which one of these agrees best with the map in this area. You can imagine with larger side chains, right, you have multiple rotatable bonds, and so you can try all different possible rotameric states and ask which of these best agrees with the map. You can potentially do this for the backbone as well, right? So we're just going to sample all possible conformational states in this local area and then pick the one that best agrees with the map. And so you can think of this sort of like, so this is the series of states you're testing, and at each state you allow the model to then relax down and settle into a local minimum, and you can ask, okay, which one ultimately best satisfies my refinement target function. A somewhat more aggressive refinement protocol is called morphing. And so yep. Yeah, those sorts of questions are always a little challenging and come down to a judgment call. If there's absolutely no way, so I think in those cases the map will almost always be ambiguous. So if the map is ambiguous, I would probably tend to go with geometry a bit more, because there will be noise in your data too, right? And so sometimes you may have a tiny hint in the map that looks like the side chain's going this way, but whether that is truly density deriving from the side chain, deriving from noise, deriving from something else, say nearby water molecule or something is a potential issue. Whereas if by putting it, so I'm saying, okay, to the right you see a little density, to the left it would just completely overlap with another atom, right? There I think it's sensible to say, okay, well, I know it's not overlapping with this other atom, but so I'm gonna put it in some place that makes geometric sense. Now, in a case where the map is really clearly showing you that the side chain should be over here, but it's going to end up clashing with something if you put it there, then I think it can often point you to something else that's wrong with the model, right? So it could mean that the adjacent part of the protein is mismodeled in some way. And so it might, it's fairly common that there'll be a sort of like domino series of changes you have to make. So you need to change the neighboring residue in order to make space for that sidechain movement that the map is telling you to make. So it is a little case by case, but yeah. Okay. So morphing is another one of those options you can check in terms of the different refinement protocols. And the idea with morphing is, it's fairly common that, say you've got 2 different data sets for your protein in 2 different conformations. You've got 2 different 3D classes. And there will be some local differences between the 2 models. So you've already built structure 1, and now you're working on structure 2, and there's this loop that has shifted position. So the whole loop is kind of slid over by 3 angstroms, right? So morphing kind of looks for chunks of your model, say like a whole helix or a whole loop, that look like they could have shifted in this way. So it tries to identify regions like this and actually move them into the map. And so So you can see here this loop that is kind of in cyan. You could imagine it fitting in the map where this density is here. Would probably be a better fit. And so morphing will basically try to take that whole chunk of residues initially as sort of like a rigid body and translate it into this new location. And then the rest of the refinement engine will try to then like make local adjustments at the junction to kind of maintain good geometry. So morphing can make fairly large changes. So it has a fairly large radius of convergence, but it is like fairly aggressive, right? And so it can also potentially make changes to the model that you don't want necessarily every cycle of refinement. Okay, so there's many options to choose from. How do you decide which of these to use in a given round of refinement, right? Because you're going to do probably multiple cycles of, you're going to build the best model you can initially, you're going to do some refinement, you're going to go back through and check eyes on every residue. I love that. Yeah, because you really do need to go kind of through your entire model. And then you're going to do more refinement, right? And each refinement job isn't necessarily the same, okay? So which parameters should you use? So I think the first question is, how aggressive do you want to be in refinement, right? So the gradient refinement, I said, is very kind of gentle, just allows the model to relax. Things like simulated annealing, morphing are, say, on the like most aggressive side of things. In the middle maybe is kind of the grid search. So in terms of deciding which of these you want to use, I think one thing I often ask myself is, how much do I trust my starting model? Okay, so you can often be in a situation where maybe there's a 2 angstrom crystal structure or a very high resolution EM structure of a large chunk of your model, and you're working now with a 5 angstrom map, right? So in that case, I trust my starting model a lot, and I trust my data modestly. And so probably a lot of the sidechain rotamers and overall geometry derived from this high resolution model probably hasn't changed. There may be some small changes, right? But my first assumption is going to be that nothing has changed. And so then I actually don't want my refinement protocol to change that model a lot, because it's most likely it's going to make it worse. So that's one factor. So how much do I trust that starting model? How much do I trust my data? So if my starting model is from a 5 angstrom structure, but my data is now 3 angstrom, I trust my data more than my starting model, and I'm more willing to kind of change up that model to agree with my data better. And then I guess the other question is, how different is my starting model from my data? So am I starting from a model that is, an experimental structure of exactly this protein, or is it, a 50% identical structure from a homolog, right? And so if I'm starting with a model that is exactly my sequence that I trust a lot, again, I'm probably going to want to change my model less. If I know I'm starting from a very divergent homolog, I know that there's going to be differences in this protein, and I'm going to want to be a little more aggressive and allow the model to change more. Okay. So those are some things to think about in terms of how you set up your refinement jobs. By using these more aggressive sorts of refinement, like morphing, grid search, simulated annealing, you have a larger radius of convergence. So that potentially means that you have to do less model building, because the refinement protocol will be able to move your model more. But the downside is that at some stages of refinement, particularly in the late stages, you might not want your model to change much. You're kind of just trying to tweak the kind of details and clean things up. And you don't want the refinement protocol going through and changing 3,000 residues in this model that you're trying to finish off and get deposited. And so then less aggressive, of course. So it will have a smaller radius of convergence. That means that it's not going to change the model as much. You might have to manually intervene more, but sometimes that's a good thing. And that would be sort of just like rigid body refinement and this kind of global minimization. Okay, and so then. So not only in terms of your start, how much you trust your starting model and how much you trust your data, I guess some other things to think about are, what stage are you in the refinement process? So at the very beginning, I told you I'd probably just kind of do some rigid body refinement. At the early stages, if you are going to take a more aggressive approach, that's the time you want to do it, right? So you've basically fit your starting models into the map. There's going to be loops that have moved. So turn on grid search, turn on morphing, and let the refinement software do a lot of the work for you. However, in the late stages, so after you've gone through 2-3 rounds of this, I would always turn off these more aggressive protocols. So I might use grid search, morphing, or simulated annealing in my first round of refinement after rigid body. But after 1 round of that, or maybe 2, in the later stages, I will turn them off, and I will only use the global minimization and the B factor refinement. And that's really just because, kind of getting back a little to your question about, say, if you have kind of weak density for a side chain, if you have weak or no density for a side chain and you turn on grid search, every time you do refinement, it's going to try to sample all the different rotameric states of your side chain and change them, right? And at some point, you may have positioned a side chain to minimize clashes with neighboring residues. You might have positioned it because, well, that position makes good chemical sense, right? So it could be making a salt bridge with a complementary charge nearby, or maybe some hydrogen bond. If you turn on grid search, all of those carefully positioned details you've done will just get scrambled again. Okay. So I hope that maybe gives a little sense of, like, at different stages of refinement, how you can maybe think about what those different parameters can do for you and how they might work against what you're trying to do. Okay, so a lot of the other options here are related to restraints. And so, we talked at the beginning about how, in addition to our data, we have to rely on all of this prior knowledge to restrain the refinement of the structure. And so we can talk a little bit about these different options. So we can restrain the secondary structure. We can use that non-crystallographic symmetry refinement restraints, reference model restraints, rotamer restraints, Ramachandran restraints. Oh, and I just wanted to point out here, there's all these kind of check boxes in the main window, but there's also all these buttons that take you to additional details, right? So for example, when you're setting up your rigid body refinement, if you just check rigid body refinement, it will take your whole PDB file and treat it like one rigid body. But if you hit this select atoms button, it will give you the option to then define multiple rigid bodies, right? Or if you're doing non-crystallographic symmetry, it'll allow you to define what those different non-crystallographic symmetry related chains should be, right? And so similarly, down here in all parameters, that will give you access to a complete list of everything you could possibly set within the refinement package. So if you're working through the GUI, these things might not always be immediately there in front of you. You can also run from the command line from a file that would have kind of all these things. You can kind of just go in and edit as well. Okay, so how do you choose which of these restraints to use? And so to some extent, the answer is it depends. What you use is really resolution dependent. And so, as I mentioned earlier, with that phenylalanine residue that we refined without any restraints and it kind of collapses. So at low resolution, we need to use more restraints. So we need to enforce proper geometry. We need to enforce secondary structure to keep the protein from kind of unraveling. But at high resolution, we can get away using less restraints. And actually, we often will get a better model in the end by using fewer restraints. And so, at the limit, at extremely high resolution, when you start getting sort of past 1 angstrom, you can let go of restraints entirely. But it's exceptionally rare to be in. I mean, I've never had a structure of like 100 plus structures. I've never had one, like anywhere near that. So I've always had some kind of restraints. And at low resolution, definitely we need to use them quite heavily. All right. So at high res, high res meaning, say, like 2 angstroms or so, you might be able to use essentially just bond lengths, bond angles, torsion angle restraints to keep your model under control. But as you get lower resolution, you need to start trying some combination of these other restraint options that are available to you. And so most often I'll probably have the secondary structure restraints turned on, and then try adding some other combinations of NCS restraints if I have NCS in my molecule, reference model restraints, which I'll talk about a little bit in a second, and rotamer restraints can be helpful, and Ramachandran restraints, which perhaps very late in refinement, I would consider turning on. Ali, do you have any thoughts on Ramachandran restraints?
Yeah, so my opinion on this is don't use them until you already know you've got it as right as you can, because otherwise Ramachandran restraints are going to hide errors, because they're going to force something to fit Ramachandran, which doesn't mean it's correct, it just means it looks good.
Yeah.
And that's the case with a lot of different restraints.
Yeah.
Ramachandran restraints.
Yeah, I feel like I have been, a little surprised that they're like so prominent in the GUI now, because I do think they are potentially cause for concern.
I don't think there's anything wrong with using them. It's just that when you're initially building a model, like if you just refine everything initially with Ramachandran restraints, it's going to suck it into the nearest region
Yep.
of torsional space that's allowed in the Ramachandran plot. But that can totally be a false minima, unless you actually look at it and figure it out. And it's a lot easier to just like build it without Ramachandran restraints, look at it, look at all the errors in the Ramachandran plot and like fix it manually.
Yep. Yeah, I completely agree, and I was just like, as I saw that check mark coming up in the GUI, it makes me like worry that people will check it from the beginning, because the Ramachandran plot we're going to talk about in a couple seconds, but it is like one of the like oldest, most useful validation metrics that we have, and so the only issue is that if you are restraining your residues to always fit the nice parts of the Ramachandran plot, then you can't really use that as a diagnostic tool to assess where your model has problems. And maybe that'll become a little more clear in a second. So the Ramachandran restraints, I agree, I would leave off early in refinement. If everything is good, I'd say you could leave them off to the end. It's not like you need to ever use them, but if you, after having corrected areas, you're having problems where residues keep slipping back into disallowed parts of the Ramachandran plot, then you can put this on to kind of help hold things in place. What's up?
So the high resolution, how often do you see that torsion angles don't agree with what you expect? I understand like the laws of physics will make sure that the restraints are enforced, but like how often does that occur where you just have some you see the high resolution density.
So like true exceptions.
Exceptions, yeah.
Yeah.
I could have just said the word exceptions.
Yeah, I mean it definitely happens. I mean for all of these metrics there will be exceptions. Say for the Ramachandran plot, so I did a lot of work on antibodies before, and so the light chain of antibodies, there's this one residue that always has. It's been a while now since I worked on antibodies, but I'm forgetting if it's a cis peptide that is. Yes, the bottom line is that there are, I'd say like on the order of like 1 in 100, 1 in 200 kind of numbers. Like it's not super common, right? And especially as you're at low resolution, you're probably very rarely going to encounter a case where you can clearly see that, but. It definitely happens, yeah. So they're not all errors, I guess, at the end of the day. So, and I think that's why it's reasonable that there's some kind of allowance for this, right? So we don't necessarily want to make a model that's absolutely perfect in terms of matching every single validation parameter, right? 100%. I mean, so sometimes I see a structure, when I'm reviewing a paper, and 100% of the residues are in the preferred regions of the Ramachandran plot, right? And it's not a real protein, it's not like a real structure. And that's a kind of case where, I know that this person put on the Ramachandran restraints like through their whole refinement protocol, and it was probably like way too tight. And, potentially masking problems in that way. Oh, does it? Oh, that's good. Because actually, I mean, I usually run from the command line. I was trying to show the GUI because I thought that might be more. Oh, that's good. Cool. Okay. Yeah. So try different combinations of the restraints, and kind of this last point. definitely, if you just turn everything on, it often can restrain the model so much that it just really can't move. And so often the best restraints won't be turning on everything, but some combination of these options, right? And so sometimes you have to play around a little bit, try a couple of refinement jobs with different combinations, and just see what seems to give the best model. Okay. I probably should talk about validation first because it's so important, and I always sort of run out of time. But validation is really important, and it's not just to make make a final model with good stats so that no reviewers question you and everyone looks at your structure in the PDB and says what a great job you did. It's really also to help you to, like, during the model building and refinement process, to make the best possible model you can. And so often things like Ramachandran outliers point not just, it's not just that like, oh, that's incorrect, but often will help you to identify an area where the backbone geometry is twisted or strained in some way. And it might not, based upon the map and fit to the map, be easily identifiable, but it can draw your attention to an area, and you can then actually figure out that you have some kind of error in this region, right? Okay, so these stats, so they one of the things I look at after each round of refinement to see, okay, did the model get better? Did the model get worse? If I'm comparing different refinement protocols, which one is yielding a better model? Help us to identify problem areas, and also to be able to assess kind of local issues, right? So things like map correlation coefficients tell us like overall how the model agrees with the map, but doesn't really tell us about local issues. Okay, so there's a whole lot of metrics we can look at and consider. So from things like model map correlation coefficients, so it's really just how well does your model fit the map. RMS deviations of things like known bond lengths, known bond angles, so are these kind of consistent with known protein structures. Unmodeled densities, right? So often we're really focused on the protein itself, and it can be easy to sort of miss nearby densities that could be peptides, small molecules that have co-purified with your protein, or perhaps like, a part of your protein from somewhere else that you didn't realize has kind of gone into a disordered region and reappeared over here and then gone back. So checking out those unmodeled densities. Molprobity is a great validation tool. And so the overall molprobity score and the clash score are both useful things to look at. Ramachandran plot, cis peptide bonds, side chain rotamer issues, and B factor issues. And so let's try to get through a few of these. I might just sort of jump around to hit some highlights. So there's very few metrics actually that tell you anything about how your model agrees with your data. So most of what we'll talk about now is really focused on kind of geometry of the model. And so there isn't really anything quite like R work and R free for a crystal structure that tells us, how well we've modeled the original data. And so one of the few things you can look at are these model map correlation coefficients. So these are kind of across a global metric for your whole model against the whole map. And there's a few different versions of these. I've got the reference here at the bottom, and so perhaps I'll leave it to you all to read a little more about these if you'd like to know more details. CC mask is probably the most widely cited one, and this is essentially looking at so a mask that is around the model you've built and comparing this with your map. And so typical values for a well-refined structure, I mean, they are quite variable, but commonly, I would say like in the kind of 0.7 to up to like low 0.8 range. So this is something that would vary from 0 to 1. And so things from 0.7, 0.8, sometimes 0.6 something. But much below that, and you might start worrying. Recently, I came across a structure in the PDB where someone had inadvertently deposited the map with the wrong hand. Fortunately, they built the model correctly, but just in the deposition process, they deposit. And there, I think the CC value was something like 0.3 or something. So it can still be like pretty far from 0, even if something is quite wrong. Okay. We've talked a lot about stereochemistry and geometry, so we know that bond lengths have a very narrow distribution, and we know that bond angles also have fairly narrow distributions. And so all refinement softwares will report an RMS bonds value and an RMS angles value that gives you some sense of how your model compares to these expectations. And these are kind of like typical ranges you might expect for a well-refined model. Some of these tools in COOT are really helpful for validation. I'm not sure if you all will touch on some of these in the tutorial today, but so there's this whole validate menu with lots of things. And so you might even just, on your first structure, march down and try everything in this menu. But unmodeled densities and unmodeled blobs is one of these that's sort of useful. You can also use this difference maps peaks section. But basically, this just allows you to identify areas of the map where you haven't modeled anything yet. And you'll get this list of all the unexplained densities, and you can cycle through and try to see, are any of these things that you can identify as potentially interesting? Maybe the ligand that you were hoping to see in your structure, or so it's fairly often that there may be some peptide or some. I've seen a few cases where so your chain will disappear, you'll lose the density, but some of it may be ordered because it's packing up against another protein. So you might see a helix that you haven't modeled that you can then account for in that way. Mole probity can give you a lot of information about a whole bunch of kind of geometry issues all at once. I actually like to run it from the website, although Phoenix also outputs a lot of this information for you just in the output of Refinement. What I like about the website is it actually gives you sort of percentiles for a lot of these stats, so you can kind of depending upon the resolution of your model. And so that can give you a, because when you're getting started, I think often a lot of these stats are like, well, what is good? Is this good or is this bad, right? And so by having this percentile associated with it, you can say like, okay, well, so my mole probity score, is 1.17. I don't know if that's good or not, but if it's the 99th percentile, then you know it's really good, right? So I would encourage you to try checking it out on the website so you can actually see those values too. The Ramachandran plot, so you can get this from COOT as well, from the drop-down menu in a sort of like interactive way. So every dot or square or triangle on here is one of the residues in your protein, and if you click on it, it will take you to that location, so you can look a little more carefully. So an ideal plot, almost all your residues will be within the colored regions of the plot. The triangles are glycines, and so actually they have kind of a special Ramachandran plot just for them because they have additional regions they're allowed. So actually if you mouse over one of these triangles, the plot will actually change to reflect the conformational distributions for glycines. So basically if everything is in blue, you're good. Here's on the right an example of a not so great Ramachandran plot. So everything that's in red falls outside the allowed areas, right? And so this can be a way to, so you can then click on each one of these, go to these, and kind of try to figure out, well, what is wrong in this area about the backbone geometry, and how can I try to adjust things to move these regions into the allowed parts of the plot? Okay. And this just illustrates for different residues, there are different regions that are allowed and disallowed, and so you can look kind of on a per residue basis. Cis versus trans peptide bonds is something you should kind of keep an eye out for. Trans peptide bonds are strongly preferred. There are occasionally exceptions, and particularly right next to a proline, you often will have a cis peptide bond. And this is just kind of not as preferred because you can have these clashes between backbone atoms. And so COOT actually has some new features over the last few years to make the identification of a lot of these kind of problems more clear. So wherever there is a cis peptide bond, it displays a kind of trapezoid like this. In this case, it's in the vicinity of, it's associated with this proline. So it's colored green because cis prolines are fairly common. But in other cases, so here, for example, is an example of a cis peptide bond that does not involve a proline. And so these are generally pretty rare. And so as you're just moving through your model with your map open, you may see these kind of segmented areas displayed. And that can clue you into kind of a local problem in this area. Similarly, these yellow regions are indicating other peptide bond problems. So not cis or trans, but strained in some way, right? So not at 0 degrees, not at 180 degrees. COOT is like incorporating more and more tools like this that just as you're going through residue by residue, you can kind of identify these problem areas.
Let me just comment there briefly on so one of the things that COOT has done recently, which I don't like particularly, it's for a good reason, but it can have unintended side effects, is it makes it more difficult to flip a peptide. And so that's generally a good thing. But the thing to remember is if you're building something with prolines, you should remember that some of them can be cis, and it will default them to trans, and you will only be able to change them if you explicitly flip the peptide from cis to trans using a fairly non-obvious tool in COOT. And so if you're getting geometrical errors around the proline, consider the fact that it might actually be a cis proline, and you might want to test that, because it is something you need to explicitly test. You can't just drag that into the density and hope that it will flip from cis to trans.
Yep.
So
Yes.
As far as I understand, the prevalence of like cis prolines is around 7 to 10% of them, right? So what would the population of like non-proline cis peptides be in proteins?
I don't have an actual number off the top of my head, but I mean, definitely less than 1%. Like, I don't know if anyone else has very rare. I'm sure there is. I mean, I would guess on the order of like, I mean, if I just had to put a number out there, like on the order of like 1 in 500, 1 in 1,000, like exceptionally rare. The vast majority of structures I've looked at recently, from our lab, I can't remember one. So there are some cases like in this antibody light chain. I'm pretty sure what I was remembering was a cis proline that is a cis peptide bond that is not a proline. So they can happen. They're often in structurally important proteins. So they're often when you have something weird like that, it will be in the active site of the enzyme or something, because they're there for a reason. But yeah, very, very rare. Okay, right, and so here's an example just where you could see that there's a cis peptide bond here, flagged by this red trapezoid, and by kind of trying to look carefully at the map, you can imagine, okay, maybe if this was cis, it would fit better and actually kind of fit this in. Okay, yeah, lots of other tools here in COOT. I'd really encourage you to check them out. So for rotamer outliers, I find this really helpful too, where it'll kind of make these plots where really low bars indicate that rotamer is great for that residue, but will flag any rotamers that are outliers, right? And so you can click on these bars, it'll take you to that residue in the protein, and you can then use the rotamer fit tools to try to find a rotamer that fits your map better. Skip over C beta deviations and ADP outliers. The last thing I just wanted to mention is an old tool that I like that, it is pretty dated, but actually it was just revived recently, called the JCSG QC server. This was developed by one of the structural genomics centers as the way that they would validate all of their crystal structures at the end of the process just before deposition. It runs a lot of validation procedures all at once, so I like it as a sort of one-stop shop. It is geared for X-ray crystallography, so if you're working on a crystal structure, then by all means you can upload your MTZ file and all sorts of other data files that'll run extra validation for you. But even if you only have a set of coordinates, it'll run molprobity, it'll run a bunch of other things. A couple of the things that really stand out to me that I'm not aware of how I would get anywhere else is, so if you're missing residues, or if there's some issue with the numbering of your sequence of your PDB file, which can cause you headaches during the deposition process, it flags these. Also, so there is very much a debate about whether you build those side chains that aren't in density or not. It's like a perpetual battleground on the CCP4 bulletin board. Like once a year, there's some major blow up about this. I usually build all my side chains, even if I don't have density for them. I think people who don't build them are okay people too. But because I always want to build all my side chains, so this tells me all the side chains that have missing atoms, or like any residue in your protein that's missing an atom. So if somehow an atom, and sometimes also during refinement, sometimes atoms will get like torn off. Maybe you like deleted something by accident. So this will kind of clue you in if there's atoms missing from your model that you might have expected. If you if you did mean to delete the side chains, great. You can say, okay, well, I'm just going to ignore that. But it's a way to kind of see that.
Would you want to use something like this to like quick check some other like apps or how other models work? Like if you read a paper and you're like, oh, I want to look into like how this model is, right? Would this be a good option?
Yeah, I like this one a lot. And because it's I don't want to go through all of it because there's a lot in here, but any sort of like clashes between atoms are in here, like lists of everything. So it's fairly comprehensive, not quite so comprehensive as probably the PDB validation report, which sometimes I find a little overwhelming. But this has really kind of a lot of useful information in one place, and it's like upload your PDB file. It takes 2 minutes to run, and so it's pretty easy too. Okay, so that's all I have. Sorry, I went over a bit too. Last slide, which will be online, has just some links to some validation tools and a couple of papers that I think could be interesting. So, thanks. Happy to answer any other questions you have.